Far across the American Southwest, two immense reservoirs stand as monuments to one of the greatest engineering achievements of the 20th century. Their shorelines trace towering canyon walls, their waters stretch for hundreds of miles or hundreds of kilometers, and together they form the beating heart of a river system that supports cities, farms, industries, tribal nations, wildlife habitats, and tens of millions of people. Yet the familiar blue expanses seen in photographs from decades ago have retreated dramatically, exposing pale bands of mineral deposits that climb canyon walls like silent records of a shrinking past. Lake Mead and Lake Powell have become symbols of a growing question that refuses to disappear. Can nature still refill reservoirs built for another climate, or has the balance permanently shifted? Among the many ideas circulating whenever unusually wet winters arrive, one appears again and again. People point to one of Earth's most powerful climate patterns and ask whether a truly exceptional El Niño could rescue the Colorado River Basin. The reasoning sounds simple. Some of the wettest years in modern history coincided with extraordinarily strong El Niño events. Massive snowstorms blanketed western mountains, rivers swelled, reservoirs climbed, and drought temporarily loosened its grip. If one powerful El Niño can produce so much water, perhaps several of them could restore Lake Mead and Lake Powell to their former glory. It is an appealing thought because it imagines that a single force of nature still possesses enough strength to erase decades of decline. Yet the mathematics behind that hope tells a far more complicated and sobering story. Understanding the answer begins not with rainfall over the deserts of Arizona or Nevada, but thousands of feet, or hundreds of meters, above sea level in the Rocky Mountains, where much of the Colorado River begins its journey. Unlike rivers sustained mainly by frequent rainfall, the Colorado depends heavily on winter snowpack. Snow accumulates across mountain ranges during the cold season, storing water naturally until spring and early summer. As temperatures rise, melting snow feeds tributaries that eventually combine into the Colorado River, supplying the water that flows into Lake Powell before continuing downstream toward Lake Mead. This seasonal rhythm has sustained communities across the American West for generations. Reservoirs were designed to capture abundant runoff during wet years and gradually release it during dry years, creating a reliable water supply despite the region's naturally variable climate. For decades, that strategy worked remarkably well, aided by several unusually wet periods during the 20th century that filled the reservoirs and reinforced confidence in their enormous storage capacity. Modern conditions have proven much less forgiving. Years of prolonged drought, rising temperatures, declining runoff efficiency, and persistent water demand have steadily reduced the amount of water entering the system. Even winters that appear impressive by historical standards often struggle to overcome the accumulated losses from previous dry years. The reservoirs have become so depleted that individual wet seasons produce visible improvements without fundamentally changing the larger picture. Against that backdrop, discussions inevitably return to El Niño. El Niño is not a storm. It is not a hurricane, a cyclone, or a single weather system moving across the Pacific Ocean. Instead, it is a large-scale interaction between the atmosphere and unusually warm ocean waters in the equatorial Pacific. During an El Niño event, sea surface temperatures across portions of the central and eastern Pacific Ocean become significantly warmer than average. Those warmer waters alter atmospheric circulation across vast distances, changing the position and strength of the jet stream, and influencing weather patterns around much of the globe. Its effects vary from continent to continent, and even from one region of North America to another. Some places become wetter than average, others become drier. Some experience warmer winters, while others endure unusually cold conditions. The exact outcome depends on numerous interacting climate patterns that operate simultaneously. For the southwestern United States, especially during strong El Niño episodes, the odds often favor increased winter precipitation. Storm tracks can shift farther south, allowing Pacific moisture to reach California, Arizona, Nevada, Utah, Colorado, and neighboring states more frequently. Mountain snowpack may increase substantially if temperatures remain cold enough for precipitation to fall as snow rather than rain. That distinction matters enormously. A winter dominated by rainfall rather than snowfall may briefly increase stream flow, but fails to create the gradual spring melt that efficiently feeds rivers throughout the warm season. Snow functions as a natural reservoir. It stores water for months before releasing it gradually, reducing immediate flooding while extending runoff well into summer. This delayed release is particularly valuable for reservoirs like Lake Powell, whose inflows depend heavily on snowmelt originating high in the Rocky Mountains. Even then, geography introduces another complication that many people overlook. The Colorado River Basin covers an immense area spanning portions of 7 American states and northern Mexico. Conditions in Southern California may differ dramatically from those in western Colorado. Arizona may receive abundant rainfall while the upper Colorado Basin experiences only modest snowfall. An El Niño that produces flooding along the Pacific coast does not automatically guarantee exceptional runoff into Lake Powell. This distinction has repeatedly surprised observers during past climate events. Meteorologists often emphasize that El Niño changes probabilities rather than guaranteeing outcomes. It increases the likelihood of certain weather patterns, but local conditions ultimately determine how much precipitation falls, where it falls, whether it arrives as rain or snow, and whether it eventually reaches rivers feeding the reservoirs. The strongest El Niño events therefore create opportunities rather than certainties. If one extraordinary El Niño can produce enormous runoff, then how many would be needed to refill Lake Mead and Lake Powell after years of historic decline? Finding a reasonable answer requires setting aside headlines and focusing instead on numbers. Before estimating how much water a future Super El Niño might contribute, it is necessary to understand the scale of the challenge. Lake Mead is the larger of the 2 reservoirs by volume when completely full. Created by Hoover Dam, it can store approximately 26 million acre-feet of water. 1 acre-foot represents enough water to cover 1 acre of land to a depth of 1 foot, or approximately 326,000 gallons, equivalent to about 1,233 cubic meters. Upstream, Lake Powell stores slightly less, but remains nearly equal in size. Formed by Glen Canyon Dam, its present storage capacity, accounting for sediment accumulation over decades, is approximately 25.2 million acre-feet. Together, these reservoirs can therefore hold roughly 51 million acre-feet of water. That figure is difficult to visualize. Imagine enough water to cover 51 million acres with 1 foot, or approximately 0.305 meters of water. In metric terms, the combined storage approaches nearly 63 billion cubic meters. Few reservoirs anywhere in the world approach that scale. Those staggering numbers explain why Lake Mead and Lake Powell have long served as the primary savings account for the Colorado River Basin. During exceptionally wet years, they accumulate surplus water. During drought, they release stored reserves to maintain water deliveries downstream. Yet savings accounts only work when deposits exceed withdrawals. Recent years have revealed precisely the opposite. By the middle of 2026, Lake Powell contained approximately 5.6 million acre-feet of water. That represented only about 1/4 of its available storage capacity. Lake Mead, although holding more water, remained far below full capacity as well, storing roughly 8 to 9 million acre-feet, or about 1/3 of its maximum volume. Combined, both reservoirs held only about 14 million acre-feet. The implications become immediately clear when those numbers are compared with total capacity. If the reservoirs together can store approximately 51 million acre-feet, but currently contain only about 14 million acre-feet, then roughly 37 million acre-feet of storage remains empty. 37 million acre-feet. That is the amount of water required simply to return both reservoirs to full capacity under present conditions. Expressed differently, the missing volume equals more than 45 billion cubic meters of water. Visualizing such an amount borders on impossible. It exceeds the annual water consumption of many entire nations. It represents decades of accumulated shortages rather than a temporary seasonal decline. An increase that appears spectacular from the shoreline may account for only a modest percentage of the tens of millions of acre-feet still needed to restore both reservoirs completely. That perspective fundamentally changes the discussion surrounding Super El Niño events. The question is no longer whether an exceptionally wet winter can produce noticeable improvement. History has already shown that it can. The real question is whether even the strongest climate events observed in modern history possess enough power to erase a storage deficit approaching 37 million acre-feet. Answering that requires examining the wettest El Niño years ever recorded, estimating how much additional runoff they can realistically contribute to the Colorado River system, and comparing those gains against one of the largest water deficits in North America. Only then does the remarkable scale of the challenge become fully visible. Historical records provide a useful place to begin because the Colorado River has already experienced several remarkably wet periods associated with exceptionally strong El Niño events. Among the most famous were the episodes of the early 1980s and the late 1990s. Both altered weather patterns across much of the Pacific Basin, strengthened winter storm tracks, and delivered substantial precipitation to large portions of the western United States. The El Niño event spanning 1982 into 1983 remains one of the strongest ever observed. California endured widespread flooding as powerful Pacific storms arrived one after another. Mountain snowpacks reached extraordinary depths in many regions, reservoirs filled rapidly, and river systems experienced runoff far above average. Ironically, Lake Powell itself became the center of an unexpected engineering challenge. The inflow was so immense that operators at Glen Canyon Dam were forced to use spillways for the first time since the dam's completion. Turbulent water damaged portions of those spillways, reminding engineers that abundance can present dangers just as serious as scarcity. Nearly 15 years later, another exceptionally powerful El Niño developed during 1997 through 1998. Once again, atmospheric circulation shifted across the Pacific, delivering unusually wet conditions to many parts of the American West. Snow accumulated across numerous mountain ranges, spring runoff increased, and reservoirs throughout the Colorado River Basin benefited from the additional inflow. Those remarkable years often become the foundation for hopeful predictions whenever another El Niño begins developing. Yet they also illustrate an important limitation. Even extraordinary winters represent only a single season within a river system measured across decades. Scientists attempting a simple estimate therefore ask a straightforward question. How much additional water can one truly exceptional El Niño contribute to the Colorado River system after accounting for reservoir operations and downstream releases? Exact values vary because every El Niño differs in strength, duration, snowfall distribution, spring temperatures, and water management decisions. No two events produce identical outcomes. Nevertheless, historical analyses suggest that an exceptionally favorable El Niño year might contribute roughly 3 million to 5 million acre-feet of additional net storage across the reservoir system under highly favorable conditions. Those figures already account for the fact that not every drop of snowmelt remains in storage. Water must continue flowing downstream to satisfy legal obligations, municipal supplies, agricultural demand, environmental requirements, and hydropower operations. Even during unusually wet years, reservoir managers cannot simply close every outlet and keep all incoming water. The estimated gain therefore reflects the approximate increase in stored water rather than the total runoff entering the river. Once those numbers are compared with the existing storage deficit, the scale of the challenge becomes much clearer. Earlier calculations showed that Lake Mead and Lake Powell together are missing approximately 37 million acre-feet of water before reaching full capacity. Suppose an extraordinarily favorable Super El Niño contributes about 3 million acre-feet of additional stored water. Dividing the total deficit by that annual gain produces an answer of roughly 12 to 13 Super El Niño events. Using the more optimistic estimate of 5 million acre-feet changes the result but not the broader conclusion. Under that assumption, approximately 7 to 8 exceptionally powerful El Niño years would still be required to refill both reservoirs completely. At first glance, those numbers may not appear impossible. 7 outstanding winters spread across several decades might seem achievable. The difficulty lies in the assumptions hidden within the calculation. Every estimate assumes that each Super El Niño performs as well as the strongest historical events. Every estimate assumes that favorable snowfall falls precisely where the Colorado River Basin benefits most. Every estimate assumes there are no severe drought years between wet periods. Every estimate assumes that reservoir operations can capture nearly all additional inflow. Every estimate assumes that storage gained during one wet cycle remains available for the next. Nature almost never behaves so conveniently. Climate variability operates on alternating cycles. Wet years are commonly interrupted by dry years. Heavy snowpack can be followed immediately by below-average precipitation. Heat waves can accelerate snowmelt, reducing runoff efficiency before water even reaches the reservoirs. Rain falling onto warm ground can infiltrate soils that have become exceptionally dry after prolonged drought, allowing large amounts of moisture to disappear before streams begin rising. Even the location of snowfall matters enormously. Many people understandably assume that heavy precipitation anywhere across the Southwest automatically benefits Lake Mead and Lake Powell. The Colorado River Basin is much more selective than that. Large portions of the river's annual flow originate in the high mountains of Colorado, Wyoming, and Utah. Snow accumulating in those elevations acts as the primary source feeding the upper Colorado River Basin. Heavy rainfall across southern Arizona or coastal California may generate impressive local flooding without substantially increasing inflows into Lake Powell. Meteorologists therefore emphasize that El Niño influences weather probabilities rather than guaranteeing beneficial conditions over the specific watersheds that matter most. Temperature introduces another challenge. A warmer winter may actually reduce the fraction of precipitation falling as snow. Instead of accumulating gradually within mountain snowpack, some storms arrive primarily as rain. Rain runs off quickly, sometimes causing flooding, but it lacks the long-term storage provided by deep mountain snow. Snowpack releases water slowly over weeks or even months, sustaining river flow throughout spring and early summer when reservoirs receive much of their annual inflow. Modern warming trends increasingly complicate that natural timing. Higher spring temperatures melt snow earlier than in previous decades. Earlier melting lengthens the warm season, during which evaporation removes water from soils, vegetation, and river channels before it ever reaches Lake Powell. Hydrologists refer to this as declining runoff efficiency. Even when snow totals appear encouraging, a smaller percentage ultimately arrives at the reservoirs. This explains one of the most surprising discoveries made during recent decades. The Colorado River today often produces less streamflow than it did decades ago, despite experiencing similar amounts of precipitation during some years. Rising temperatures increase evaporation and plant water use throughout the watershed, quietly reducing the volume available for downstream storage. Those processes mean that the mathematical estimate of 7 to 13 Super El Niño events should never be interpreted as a realistic forecast. Instead, it represents an idealized exercise designed to illustrate the immense size of the storage deficit. Imagine attempting to fill a giant reservoir while someone continuously opens a drain at the bottom. Adding water certainly helps, but the reservoir gains much more slowly than expected because losses continue every day. Lake Mead and Lake Powell function in much the same way. Water enters through river inflows while simultaneously leaving through controlled releases, municipal consumption, agricultural irrigation, industrial use, evaporation, seepage, and environmental requirements. Consequently, each exceptionally wet year begins not from zero losses, but from an already active system that continues consuming water regardless of weather conditions. That distinction transforms the entire discussion. Instead of asking whether one extraordinary El Niño can refill the reservoirs, the more meaningful question becomes whether repeated wet decades can outpace the combination of human demand and climatic losses. Recent history already offers an important clue. The remarkable snowpack during the winters of 2022 through 2023 ranked among the strongest seen in decades. Rivers surged across much of the upper Colorado Basin. Reservoir levels responded noticeably. Boat ramps reopened. Previously stranded marinas regained access to deeper channels. Headlines celebrated the dramatic improvement after years of relentless decline. Yet despite one of the most impressive runoff seasons of the modern era, neither Lake Powell nor Lake Mead came anywhere close to full capacity. Within subsequent seasons, continued water use, evaporation, and less favorable weather gradually reduced much of those gains. That outcome demonstrates why weather alone is no longer sufficient to erase decades of accumulated deficits. One extraordinary winter can slow the decline. Several consecutive wet years can stabilize conditions for a time. Completely restoring both reservoirs, however, requires far more than repeating the strongest El Niño events recorded during the past century. The mathematics may suggest 7 to 13 ideal Super El Niños under perfect circumstances, but the real Colorado River operates under far less forgiving rules, where every additional gallon, or approximately 3.8 liters, must compete against an increasingly thirsty landscape.